Hello and welcome to module 4 on source coding. Let us look at the outline for today's presentation. We will start with variable length codes, then we will follow it up with Kraft inequality, then we will talk about the source coding theorem, and finally we will discuss what do we mean by the efficiency of a code. But let us start with a quick recap of what we have done and we will refresh our memories. So, what we have done so far is we have looked at information measures for continuous random variables, wherein we looked at the notion of differential entropy. We will quickly revisit it again. Then we talked about average conditional entropy for continuous random variable. Then we measured the similarity between two distributions in terms of relative entropy, which is also called the Kullback-Leibler distance. We looked at the asymmetry of that and then looked at Jensen-Shannon distance, and finally we introduced the notion of prefix codes. So, let us start a quick memory refresh. We started off with self information of the event x is equal to x I, which we saw had a logarithmic measure for information. Then we said that it is important to have the average self information, also called entropy, defined as h of x, right. So, it is with a negative sign p x I log p x I summed over all possible occurrences. We also defined mutual information between x is equal to x I and y is equal to y j. So, between two events as x I of x I semicolon y j, and we found out that it is mathematically equivalent to the mutual information between y j semicolon x I. This we realized could also be negative. Then we looked at the definition of average mutual information, which is I capital X semicolon y, which is defined with a double summation, and we also discovered that this quantity is non-negative. We then moved to continuous random variables, where we defined the differential entropy denoted by small h of x as follows. But we emphasized again and again that there is no physical meaning attached to it. So, I can plug in the value of p of x and compute it, it will come out to be finite, but we all know that the average self information for a continuous random variable is indeed infinite. Therefore, differential entropy really does not have a physical meaning attached to it. We also looked at the chain rule for differential entropy given as follows. After that, we asked ourselves a question: how do you say how similar are two probability mass functions p x and q x, and we defined the relative entropy, also known as the Kullback-Leibler distance, d p parallel q, as follows. And it can be seen as simply the expected value of log of p x over q f x. So, it goes without saying that if p x equals to q of x, log 1 is 0 and there is the distance reduces to 0, that is, there is no difference between the distributions p and q. On the other hand, a quick observation of this equation tells us that this is not symmetric. That is to say that d p parallel q is not the same as d q parallel p. This is important to note, and therefore, it does not follow the symmetry property. We also found out that this relative entropy or the Kullback-Leibler distance does not satisfy the triangle inequality. So, it does not follow two of the three requirements for a distance measure. It is only non-negative. It does not follow the symmetry property or the triangle inequality. To overcome this problem of symmetry, Jensen-Shannon distance was defined. Again, it is the distance between two probability mass functions Px and Qx, and it is defined as follows. And we found out that if the base of the log is 2, then the Jensen-Shannon distance lies between 0 and 1. In literature, this Jensen-Shannon distance is also called Jensen-Shannon divergence or sometimes information radius. But why are we doing all of this? Well, our ultimate aim is to efficiently represent symbols. We would like to code them so that we use minimum number of bits to represent the symbols. For that, we defined codes and code words. So, a code is a set of vectors called code words, and we could have a fixed length code, for example for the English alphabet, and since we have 26 letters, about 5 bits should suffice, because 2 raised to the power 5 is 32. So, we will have some additional code words available, but a fixed length code should suffice for an English alphabet. However, there is a simple observation that we can make. Not all letters are equiprobable. What does it mean? We should not really allocate equal number of bits for less probable as opposed to more frequently appearing letters. So, there could be a better strategy than to allocate equal number of bits for all the letters in the English alphabet. So, we start off with an example. We did it in the previous class as well. We have only the first 8 letters in the English alphabet. For this example, A, B, C, D, E, F, G and H, and the simplest and the most obvious thing is 8 letters, no problem, 3 bits per letter, we have 8 possible code words. So, code words are from 000 up to 111, and this set of code words is called a code. So, in this table we have the fixed length code, but nobody stops us from making a variable length code. And how do we do that? Well, a particular example is as follows. I have A being represented as 00, just 2 bits, B with 3 bits, so and so forth, and since we ran out of 2 bit or 3 bit, we could also say that G and H also have 4 bits. So, it is clearly a variable length code. It goes without saying that there are several possible variable length codes available for these 8 letters. So, let us take a toy example, a bad cab. We would like to encode it. So, if we use the fixed length code, we can use it to encode it and we get 21 bits, whereas for the variable length code we have only 18 bits to represent a bad cab. So, we have fewer number of bits actually representing the variable length code, right. So, we would like to now see, is this the only possibility or what else can be done for representing a bad cab. Okay. May I request somebody to please close the door? Yeah. Okay. So, we get back to this example of a bad cab, right. So, let us try another possible variable length code. So, here we are trying to be more aggressive. Again we have A, B, C, D up to H, and instead of 2 bits or 3 bits we start off with 0, 1, 0, 0, 0, 1, and this appears to be even more efficient because we are using fewer number of bits to represent it. Okay. So, just compare the variable length code 1 and variable length code 2, and we come up with this remarkable observation that the second variable length code actually needs half the number of bits for this particular case, a bad cab. But let us see, is this true, is this good enough? Is there a problem with this representation? So, we come to the question of uniquely decodable codes. Even though the variable length code 2 had only 9 bits to represent a bad cab, when you come to the other side of the table and decode it, you are in trouble, because simply we have several possible decoding. You could have A, EAB, AAD, or another decoding possible AB, AAB, because we really do not know when does one code word end and one code word begin. So, in today's lecture we would like to see, is there an efficient way to do variable length codes which are uniquely decodable. So, let us revisit variable length code 1 and code 2. We established that with variable length code 2 unique decodability is not a possibility, but for variable length code 1 you can see that no code word forms the prefix of any other code word. So, let us emphasize that no code word is a starting point of any other code word. For example, if you consider A, it is 0 0. Now, you can go through the entire list, no code word begins with 0 0. If you look at any other 0 1 0 for B, no code word starts with that. Now, this means that no code word is a prefix of any other code word. Consequently, the moment we receive a code word which is valid, which belongs to this set, we declare it as received and we proceed further. So, decoding is possible. This condition is called prefix conditions, and such codes where no code word forms the prefix of any other code word, they are called prefix codes. We also saw that such codes can immediately give you the answer, give you the decoded symbol stream, and hence they are called instantaneous codes. Now, let us look at a very interesting inequality called the Kraft inequality. A necessary and sufficient condition for the existence of a binary code with code words having lengths n1 less than or equal to n2, so and so forth up to n sub l, which satisfies the prefix condition is as follows: summation over all possible code words 2 raised power n minus k is less than or equal to 1. This inequality is called Kraft inequality. For non-binary case, for alphabet size of m, we have the same equivalent Kraft inequality with 2 being replaced by m as follows. We will use this extensively in our lecture. Now, let us consider the construction of a prefix code, because they are great, they are instantaneous, they are uniquely decodable. So, it is better to find out how we can make or construct a prefix code using a binary tree. So, we start with a mother node and proceed towards terminal nodes of a binary tree. So, what is a binary tree? So, let us have a look at it. We can go horizontal. So, we can have a mother node, and we can always have 2 daughters, and either we take a 1 going up, 0 going down, and so forth. So, this is a binary tree and it can go on forever. Right? So, there are always 2 branches emanating from a binary tree. But let us take this a little further, and if we say, okay, this guy is 1 and this is 0, and then we go up here and we add 1 to this 1. So, we get 1 1, and we can add a 0 because we went down, we can add 1 0, and then 0 1 and 0 0. So, what are these? These are our options. Options for what? Options for forming code words, because I can then go further down and have right from 1 1 1 going down up to 0 0 0. As we go down the depth of the tree, the length of the code word increases. So, this is the possible length. So, we are dealing with a variable length code. So, our problem of finding code word tantamounts to choosing some of the nodes within this tree, because each node is associated with a bit pattern which forms our code word. So, let us understand the prefix code from this binary tree. So, let us look at this daughter node, and from there we have, so from the mother node we have 2 daughter nodes, and then they multiply, they grow exponentially, and we have this neat looking binary tree. Now, comes the question of labeling of the branches. So, it is our choice, we can label the upper branch 0, lower branch 1, or we can exchange it without loss of generality, and we can label the upper branch 1 and the lower branch 0. And then we can label the nodes as being code words, right. So, we have labeled in the previous one n 0 0, n 0 1, n 0 1 0, n 0 1 1, n 0 1 1 0. So, basically n 0 happens to be the mother node, and whatever branch we are taking, we add that branch label to the name of the node. So, this is n 0 1 and so on and so forth. I went up over a 0 branch, I added n 0 1 0 and so on and so forth. So, we keep going and we follow it, and we can now have a possibility of understanding how to have a prefix code. So, what is the constraint for a prefix code? No code word is a prefix of any other code word. So, let us start somewhere. Suppose we have 4 symbols to encode. So, we go to the first daughter node. Of course, we could have also gone on this side, and let us declare this one n 0 0 as one of the valid code words. Now, what we observe in a binary tree is that whenever we go below onto the further depths of the tree, we keep adding 1 0 0 1, but since we are adding, we lose the condition of being prefix. So, if you have declared the node n 0 0 as a valid code word, no daughter nodes below it can be valid nodes for code words. So, we have to kind of wipe them off the screen and make sure that we never use any of these daughter nodes here, because we have declared this one. So, half the tree is gone, but we have the other half left, since we would like to search the prefix codes within these trees. So, we proceed further, because of the 4 code words we want, we have only found one. So, we proceed. So, we proceed to the next level and we declare another valid code word as belonging to the node n 0 1 0. Once we declare it, the prefix condition requires us to declare any of the daughter nodes from this point onwards invalid. So, we again kind of wipe them out from the board, and once we have declared these two as valid code words, we have nothing left here. But then we still have the quarter of the tree left, and we proceed further. And with a sign of relief, we see that we still have 2 nodes left, and so we declare these 4 as valid code words. Please note, if we had to encode 5 symbols, we could not declare the results right at this stage, we should have to go deeper into the tree. The point to be noted in this example is that all valid prefix codes can be picked up from this tree, and I can easily extend this example to an emery tree for non-binary codes, but let us just focus on binary codes here. Now, the question is about the Kraft inequality. Does it really hold? And we can check it. So, the Kraft inequality, if you go back and see, it is an upper bound summation over all possible code words 2 raised to the power minus n k. What is n k? Is the length of the code, the length of the code word, because it is a variable length code. So, different code words will have different lengths, and the summation should be bounded by 1. So, we let us check this case for the code we just constructed. So, within this binary tree, we have constructed a prefix code having 4 code words, and they are 0, 1 0, 1 1 0 and 1 1 1. So, length equal to 1, length equal to 2, 3 and 3. So, if you substitute it in this Kraft inequality, so we substitute the length of n k. So, 1, 2 for the second one, 3 and 3, we add it up, you get 1. So, the inequality is satisfied. Now, we come to a very important theorem called the source coding theorem. It deals directly with the amount of compression we can achieve. So, let x be the ensemble of letters from a discrete memoryless source with finite entropy h of x, and the output symbols be x k, where k is equal to 1, 2, 3 up to L. So, we have got L distinct symbols, and these symbols are not equiprobable. Please note, we have already guessed intuitively, if the symbols are equiprobable, compression is not likely. Why? Because we have to allocate equal number of bits to all of the symbols, but only in the cases when the symbols are non equiprobable, we have the possibility to tweak. So, the source coding theorem tells us that it is possible to construct a code that satisfies the prefix condition and also has an average length that satisfies the following inequality. This r bar is the average length, okay, and it says that the average length for this, for the symbols from this DMS, is lower bounded by the entropy of the source h of x and is upper bounded by h of x plus 1. Please note, units are bits. So, it has far reaching consequences. It tells you the absolute limit to which I can compress the symbols emanating from the source. So, let us quickly look at this theorem and consider the lower bound of the inequality. So, in order to prove that, let us start with h of x minus r bar. So, we are trying to prove the left hand side h of x less than or equal to r bar. To do so, we start with h of x minus r bar and we substitute these values. So, h of x is nothing but p x log 1 over p x, and r bar, which is the average code word length, is nothing but n x, the length of the code word k, and multiplied with the probability p x k, and this gives the average code word length. You group them together and you get this expression. Now, we have another inequality ln x less than or equal to x minus 1. So, we would like to substitute it, but before that we must change the base of the log. So, we get outside log to the base 2 e and this log gets replaced by ln. So, this ln and this quantity is x. So, we replace ln x by x minus 1 with an inequality. So, here you get the inequality and you get x minus 1, all right. And then if you take this p of x and multiply it out and carry out the summation, clearly this minus 1 with p of x, all probabilities added up adds up to 1, and pxk cancels out and you have this summation k is equal to 1 through L 2s by n minus k, and this is clearly less than 0 from the Kraft inequality. So, what is less than or equal to 0? H x minus r bar is less than or equal to 0, and consequently you have this left hand side h of x less than or equal to r bar. Now, let us consider the upper bound. So, first let us select code words of length n k such that 2 s power minus n k less than or equal to the probability p of x k less than or equal to 2 s power n k plus 1. So, we are hoping that we can do so. In due course we will find out that indeed we can do so. So, just consider the left hand side of this. What are we considering? 2 s power n minus k less than or equal to p x k. Now, summing both sides from k is equal to 1 through L, right, we get that indeed this is the Kraft inequality, and hence whatever we thought in the beginning we can do so. Now, consider the right hand side p x k less than or equal to 2 s power minus n k plus 1. We take log on both sides. So, it becomes log to the base 2 p x k, and of course, log to the base 2, hence this 2 goes away and we have minus n k plus 1, and we reshuffle it and we can write n k is less than or equal to 1 minus log to the base 2 p x k. Now, what do we do with this quantity? Well, we multiply this both sides with p x k. So, we have p x k multiplied with n k, here p x k minus p x k log to the base 2 p x k, and if we sum it over all k is equal to 1 through L, on the left hand side we have p x k n k summation, again summation p x k, and we have this summation. But suddenly we can see a very simple formula emerging from it. This left hand side is nothing but the average code word length r bar, and it is less than this quantity which is 1 plus this is the entropy. So, you can show the upper bound for the source coding theorem. So, lower bound was proved using the Kraft inequality, and we also use the Kraft inequality in parts for the upper bound. So, what is the implication of the source coding theorem? First and foremost, remember we use the condition of the prefix code. So, the source coding theorem deals with codes that satisfy the prefix condition. Okay? So, what does it tell us? It tells us something about the minimum number of bits required to represent source symbol. It gives us the lower bound and upper bound. So, it says that the minimum number of bits required to represent source symbols on an average, because remember we have used h of x, which is the average self information. So, always it will never happen, but on an average the minimum number of bits required to represent the source symbol must be at least equal to the entropy of the source. That means a source with a larger entropy would require larger of number of bits to represent it. It fits in very well intuitively, but we also have this upper limit. The upper limit says that if you are using prefix code, then you are not too far away from the best you can do. What is the best you can do? H of x. You are only one bit off. So, even though a prefix code may or may not be able to achieve the lower bound, it will never be too far away from the best you can do. Prefix codes are good. That is the take home message. Wherever possible, use prefix code. So, it also tells us that if we have found a prefix code that already satisfies this condition r bar is equal to h of x, abandon further search. You can't better this. You have hit rock bottom. You can't compress it any further. And this also tells us that a source with higher entropy uncertainty requires on an average more number of bits to represent the source symbols. So, let us take an example. I have source A and I have source B. What is my source A? We take our favorite example, a person tossing a coin, okay, and let us say he is tossing a fair coin. So, 1, 0, 0, 1. How does he give these answers? Head speaks out 1, tail speaks out 0 and keeps tossing, that is his only aim in life, tossing a coin and calling out 1, 1, 0, 1, 0 and so forth. But there is this guy B called source B, habit of chewing on a gum, sticks a gum on one side, the coin becomes weighted, unfair coin, still tosses the coin and he reads out 1, 1, 0, 0, 0, 1 and so on and so forth. But these two sources, even though are emanating 1 bit say every 1 second, should not require equal number of bits to represent the outcomes, because source coding theorem says that look, the entropies are different. So, we go back to our entropy map. So, binary entropy function, on the x axis we have p, the probability of occurrence of head, and on the y axis we have the average self information entropy h of x, and we let us mark the position of source A. So, source A who is tossing a fair coin sits at the top of the curve with h of x equal to 1 bit, but my chewing gum friend source B who is tossing a biased coin sits somewhere low. So, source coding theorem tells us that if we figure out a way to efficiently represent the source B symbols, we only need roughly 0.7 bits on an average, not 1. But here is the dilemma. Source B every second tosses the coin and shouts 1, 0, 0, 0, 1, but he should actually be shouting information equivalent to 0.7 bits. He is using the entire 1 bit. He has to do things differently. Maybe he has to toss 2 times and then speak out the output in an encoded manner, or possibly toss 3 times and whatever is the observed output should speak out in terms of an encoded bit stream. So, clearly source coding theorem tells us that hey, it is unfair to allocate 1 bit per second to source A and also 1 bit per second to source B, where these are the 2 guys tossing a fair and an unfair coin once every second. Now, let us talk about the efficiency of a prefix code. Clearly, we cannot go better than h of x. So, efficiency is a ratio which is less than or equal to 1, and eta is given as h of x divided by r bar. So, it is clear from source coding theorem that eta is less than or equal to 1, and it kind of represents the compression of data which is possible. This is routinely used for compressing speech, text, image, audio, video, and so on and so forth. So, how do we do, for example, speech compression? So, let us look at it. So, we have a person who is speaking on a microphone, and we have a waveform, hello, how are you? And so, you first have to digitize it. For that, we sample, and whatever the values are there, we quantize, and these values need to be quantized in terms of 1001, 0100, 0001, and so on and so forth. Suppose I use 4 bits per sample. But how do we compress? Well, to compress, we have to find out, is there anything which is more frequently occurring vis-a-vis less frequently occurring. So, we observe the waveform in time, and we look at the amplitude, and we are curious because it is random. Why do not we form a histogram of amplitude? So, if we see that it jumps above 0 and below 0, and this is my 0, and this amplitude could be in volts, and we can possibly have a distribution. And this distribution tells me that for this particular case, my friend sticks normally around the 0 and once in a while screams, and therefore, the amplitude goes up. But he is a generally soft spoken person. So, it is a higher probability that my signal should lie close to 0 as opposed to having very high or very negative voltages. But it is a continuous random variable, so we partition it. And we find the area under these curves, which will tell us how much is the probability of occurrence. As is clear from this diagram, that the probability of occurrences for different segments are different. So, it is clear that low amplitude signals are more probable than high amplitude signals. So, we should use fewer number of bits to represent low amplitude signals, and so on and so forth, and the rarely occurring values should probably be represented by more number of bits. In fact, I can do a prefix code for different amplitude levels and thereby get compression. So, what we did earlier was not the best way, because whether it was a high amplitude value or a low amplitude sample, we were assigning equal number of bits. Unfair? We can do it better by observing what is more frequent and what is less frequent. We can do the same for text. We already looked at an example of your English alphabet with 8 characters. We can also do it for video, audio, speech, text, whatever you want. So, let us look at an example. Consider a source x which only generates 4 symbols. Now, is it a practical source? Well, this is a source which generates 4 voltages, So, it could be a practical system, but these symbols are not equiprobable. So, I have put Px1 not visible equal to 0.5, second symbol occurs with probability 0.3, 0.1 and 0.1. So, first we would like to see what is the best we can do. H of x, plug in the values, I multiply it out and I get 1.685 bits. This is the entropy of this source. Now, 4 symbols, we have already done the binary tree example. We have 4 code words which are forming the prefix code 0, 10, 110 and 111. So, what is the average code word length R bar? We plug in nk pxk summation of k equal to 1 to 4 and we get 1.7 bits. As expected, R bar is greater than 1.68 bits, right, but not too far, because we already know that my R bar will be pretty close to h of x. If we talk about the efficiency of this code, we calculate this ratio 1.685 over 1.7 and it is pretty good, 0.9912. Now, suppose my symbols were different. Suppose instead of 0.5, 0.3, 0.1 and 0.1, I tweak them and it becomes 0.5, 0.25, 0.125 and 0.125. You add them, they add up to 1, and this time I plug in the value into my R bar. What is R bar? Nk pxk summation over k. I get the value 1.750. If I plug in these changed probabilities into my expression for h of x, nothing but minus px log px, I am surprised to see that R bar is equal to 1.75 bits is equal to h of x. We have achieved the lower bound. We have achieved the efficiency equal to 1. So, what is strange about this condition? Why were we able to achieve this? Well, it is easy to understand what is happening. Look at these probabilities. P x 1 equal to 1 by 2, P x 2 equal to 1 by 4, P x 3 equal to 1 by 8, P x 4 equal to 1 by 8, and they add up to 1. Now, if you look at the average self information of this entire code, which is h of x, right, you get 1.75 bits. But what is this average self information made out of? It is made of self information. So, let us look at the self information. Because x 1 occurs with probability 1 by 2, but what is the self information? How much respect does it command in terms of the bits? Well, it is log 1 over p x 1 equal to 1 bit. So, if you look at this guy, you will get log 1 over p x 2 equal to right, and so forth. So, you get 3 bits and 3 bits. This is the information contained in these occurrences, but they do not occur with equal probabilities. They occur with 1 by 2. So, if you multiply 1 by 2 into this plus 1 by 4 into this, 1 by 8 into this, 1 by 8 into this, you get exactly this quantity. Now, the good news is that I will use the more likely event, probability 1 by 2, to be represented with fewer number of bits. And since this is an integer, I can have a 1 bit representation for this. So, as we had in the previous case, we assign this as a 0. Most frequently occurring, minimum number of bits. How many? Well, self information is 1 bit, I have given it 1 bit. What about this guy? Well, its self information is 2 bits, so I give it 1 0. I give this guy 1 1 0 and 1 1 1. So, the only reason I could achieve the lower bound is because this self information is an integer, and I have only the luxury to allocate a full bit or 2 bits or 3 bits to a certain outcome. I cannot, if this had come out to be because of its probability 0.75, there is no way I can offer a 0.75 bit long code word. The code word length has to be an integer 1, 2, 3, 3 and so on and so forth. And therefore, because of this very unique choices of probabilities which have the self information being integers, I have been able to achieve the lower bound, of which R bar is equal to h of x and efficiency equal to 1. Okay. So, this is important to see where we are. So, in most of the cases we will be far away from h of x. So, now we kind of summarize what we have learnt today. We started off with variable length codes because that set the premise for the source coding theorem. We looked at 2 different variable length code and we saw that one of them was uniquely decodable, the other one was not uniquely decodable. Then we looked at Kraft's inequality, followed by the source coding theorem, which tells us the absolute minimum we can go for compression, and finally we looked at the efficiency of code. So, that brings us to the end of this module.